Alrighty, so the next question I want to ask is, where does bold fMRI come from with respect to whether it's generated more in and around capillaries versus in and around larger venules? So you're seeing here a depiction of the arterial venous interface. So there's a large artery feeding oxygenated, for the most part, blood into the capillaries. And capillaries obviously are half and half, arterial side and venous side, right? And then, and these branch very profusely into brain tissue, of course. And then on the other side, you see the draining veins, which sort of collect the blood passing through the capillaries and then drain it away. Now, the reason this is an important question is the following. If you think of it, if you and I were inventing bold, or perhaps just fMRI, we would really want it to be about the capillaries, because capillaries, as I said, branch very profusely into the brain, and each capillary reaches a really tiny, tiny piece of the brain. So if bold comes from capillaries, it tells me something about how precise the link between the vascular system, which is what I'm using to look at neural activation, and neural activation is. If bold is about capillaries, then it tells me that I'm very precise with the co-localization of the things in and around blood vessels that give rise to the bold signal and the underlying neural activity. On the other hand, if bold comes from, let's say, these slightly larger venules, then it means that, in a sense, the co-localization of the vascular events that give rise to the bold signal and the underlying neural activity is just, from a topological point of view, from a brain geography point of view, they're not that tightly connected. So this is very important because ultimately, whether bold comes more from the capillaries or larger venules, it is a statement about what's the ultimate resolution that bold could offer. And you can see here on the left side an actual picture of the vascular system. You can see a vein up here, a draining vein, an artery, feeder artery down here. And then if you look at the picture below, you can see all these smaller blood vessels, which are capillaries. So if you think of it this way, right, if you look at this, if the signal I receive comes from this big vein, it means that I'm probably, this vein is collecting blood from a relatively larger part of the brain. So if the signal I see comes from this vein, it tells me that the activity happened somewhere in all the parts of the brain that this vein is collecting blood from. On the other hand, if the signal comes from these capillaries, and each capillary is really feeding small parts of the brain surrounding it. So, for example, if I were to see that the bold signal really comes from this Y crossing of this capillary, it would tell me that the neural events that are triggering this bold signal must be from somewhere nearby here. So again, ultimately, this might be the limit of bold fMRI resolution in terms of understanding where in the brain something is happening. All right, so let's ask this question. Where exactly is the bold signal coming from in terms of the size of the blood vessels that give rise to the bold signal? So let me show it this way. I'm portraying two things here. On the left, I'm portraying, and we've already seen this kind of depiction. I'm portraying here a small capillary, and you can see, so in the middle, this is the blood vessel, and we sort of, we cut through it, and we're looking at it straight on. So we're looking at the cross section of the capillary, and inside it, there's some deoxyhemoglobin, so it's creating a warping in the field. And you might remember from the previous video that the color in this graph is an indication of the strength of the magnetic field in that position. So if it's all even, it means that protons here are resonating at the same Larmor frequency. If instead you see changes in color, for example, in these warpings, then protons here would resonate at a different Larmor frequency than protons out here, right? Okay, and here we have the same thing, except it's a venule. And so you can see that it's a larger blood vessel. It also creates a larger warping in the field. So let's look at this graph. Okay, so this graph is showing on this side the typical percent saturation of blood vessels. And you will notice that capillaries right here tend to have a higher on average saturation than larger venules down here. Capillaries live between 80 and 85% of saturation, of oxygen saturation, whereas venules veins and venules live somewhere between 60 and a little over 70% saturation. Now, these two conditions, obviously there is deoxygenated hemoglobin, right? And that's why we see this, that's why the field is not smooth and you see this warping here and around the capillary. So inside both blood vessels, here and here, there is some deoxyhemoglobin. This line here is telling you what is, this line here is the rest line. So if there is deoxyhemoglobin, this line tells you, for example, that for capillaries, the amount of attenuation in T2, in other words, how much faster does the T2 signal decay, or how much faster do protons dephase with respect to each other, with respect to whether, with respect to if this were entirely homogeneous. Okay, so if you imagine that there's no blood vessel here, this is all exactly the same shade of gray, that would be up here. This line tells you if there is activity in the, if there is deoxyhemoglobin around, right, how much faster do protons dephase? And this point right here tells you that in capillaries, protons dephase just about 3% faster when there is deoxygenated hemoglobin as compared to if this were perfectly smooth with no blood vessel. Okay. Now, what happens with activity? Well, see, suddenly a lot of oxygenated hemoglobin has gone here, right here. So here, this is where we started. Now, oxygenated hemoglobin comes here, and suddenly the field around the blood vessel is now very smooth, right? And that is this line up here, the active line. So some neurons have were triggered to increase their neural activity. And so what happens is that more oxygenation and metabolism goes here, and the warping in the field decreases. Right? So around the blood vessel, the warping in the field has decreased. So in terms of our capillary, we were here, and we were saying, well, when there is deoxygenated hemoglobin, protons dephase 3% faster. When there's no deoxyhemoglobin, protons dephase much slower. Right? Really, they dephase less than 1% faster than if this were not here, and everything were exactly the same shade of gray. So this is how big the change is between rest and active around a capillary. Now let's do the same, but with the venule. So you can see that when the venule is, when there is deoxyhemoglobin, so at rest, so-called, the signal attenuation, let's just pick the average of the range, is just about 5%. So the signal dies off 5% faster because of this warping compared to if this were fully gray, the same gray. Now, let's say that some activity happens, so a lot of oxygenated hemoglobin goes here, the field becomes very smooth. What happens to the protons? Well, they will all be resonating at a much more similar Larmor frequency. And so it will take longer for protons to dephase. And that's what you see here. So we started here with proton, because there was the warping protons were dephasing a little bit faster. And now, because the warping has mostly gone, protons are dephasing, take much longer to dephase. And you can already notice that the change between how much faster protons dephase when nothing is happening, rest here and here for the venules and capillaries, versus the dephasing that happens when something is happening, when there is neural activity, and so there is more oxygen saturation inside the blood vessels. You can see the magnitude of the change is much larger around larger blood vessels than capillaries. And if you were to look at inside the blood vessel, so here there's plenty of oxygenated and deoxygenated hemoglobin, the idea is exactly the same, but the change is just much, much larger. Look at the scale. So for capillaries, we're going from maybe a 20% reduction in how much faster protons dephase when they are at rest, when there is no increase in oxygen saturation. And then it goes up to just about maybe 95%, 90 to 95%, meaning protons all start dephasing much slower compared to before when an active task happens and neurons increase their activity. Now look at what happens inside larger venules. For starters, at baseline, protons dephase almost 50% faster than if this were a perfectly smooth field. Okay, so baseline means that there is deoxyhemoglobin, and here there's a big, right here there's the warpings, but inside, so in the intravascular component, there's tons of deoxyhemoglobin in here. So the signal, the protons inside the blood vessel dephase almost 50% faster than if there were no deoxyhemoglobin in here. Then neural activity happens, a lot of oxygenated hemoglobin gets inside the blood vessel and is sent to that part of the brain that is having neural activity. And so there's this increase in oxygenation, which also means that protons will go much more together. So now protons only dephase, let's say 20% faster than if this were completely gray, the same shade of gray. So here we have a change from 50% to 80% in terms of how fast and slow protons dephase versus this tiny change from 80 to 85%. So again, we've seen sort of both around the blood vessel and inside the blood vessel, the change in and surrounding venules between rest, when there is deoxyhemoglobin, and task, when there's less of it, is so much larger around the venules and inside the venules than it is inside and around capillaries. So it makes sense that probably the bulk of the bold signal is actually coming from inside mainly and around larger venules compared to capillaries. Let me show this in a different way. So this is the same depiction right here, but now I've also put all the protons. And remember, I am using color to indicate the Larmor frequency of protons. So if protons have the same color, it means they're going at the same Larmor frequency. And if they go at the same Larmor frequency, it means it takes longer for them to dephase because they're all resonating at the same pace. So let's start with the capillaries. So for starters, I think these are some 50 plus protons. So for starters, notice that only 8 protons are affected by the warping. So here we are at rest. So there is deoxygenated hemoglobin, which is creating the warping in the field. And just notice that for starters, only 8 protons are affected by it inside this whole voxel. So how would you imagine the signal be? Well, all the other protons are all resonating together at the same Larmor frequency. So the signal ought to be pretty strong. It's only, I mean, there are some, 40 plus protons all resonating together, and then there's some 8 that don't. Okay, so the signal probably is pretty strong, even though we are at rest. Conversely, look at the venules. It's the same 50 plus protons, but now we have, I think, 20 or 22 protons that are all affected by the magnetic field because there is deoxyhemoglobin in here. So now we're almost half of the protons are swinging at the orange radio frequency, and the other half are swinging at several different Larmor frequencies. I should say, although I colored all of these the same color, those that are in the black part of the warping of the field are going at a completely different frequency than those that are in the white and in the light gray parts of the depiction. Okay, so I just didn't show that, but keep in mind that these protons and these protons are going at completely different Larmor frequencies. So, given the number of protons that are affected by the warping of the field, how would you imagine the strength of the signal around the venules be compared to capillaries? Well, now there are all the orange protons going at one frequency. The lighter protons are going at different frequencies, so they're probably going to lose phase or dephase much faster. And indeed, the signal around venules at rest, so when there's no particular overt activity going on, so the basal signal from venules is a little bit smaller than the one around capillaries. Now, let's say that suddenly you show your participants some stimulus and a part of the brain becomes neurally active. Let's start with the capillaries. If you look at the image down here, now the neurons surrounding this capillary start becoming more active with respect to before. So there's a metabolic response. So more oxygen is delivered to this part of the vascular system and this part of the brain. Look at the field. Look at what happens right here. Now suddenly the field becomes much more smooth because we've displaced, we've washed out the deoxyhemoglobin, at least a good part of it, and replaced it with oxyhemoglobin, which, as you know, is diamagnetic and doesn't create those warpings in the field. So what's going to happen to these protons that earlier during rest were going at a different Larmor frequency? Well, now most of them are going at the exact same Larmor frequency as all the other protons, because there aren't those big warpings in the field anymore. And maybe a couple, particularly those intravascular, are still going at a different Larmor frequency, let's just say. So what's happening in terms of this graph? How do you think the signal would be now compared to rest? Well, obviously, because even more protons are going at the same Larmor frequency, it means that it will take longer for the signal as a whole to die off. It will take longer for protons to lose phase or dephase with respect to each other. And so the signal that we get during task around the capillary is now a little stronger than it was to begin with when there was much more deoxygenated hemoglobin. And this, as you remember, is the signal, or the blood oxygenation level dependent signal. It's a signal that depends on the level of oxygenation inside blood. The more the oxygenation, the stronger the signal. Now, let's do the exact same exercise, but around the venule. So here we are, and as I said, as we discussed a moment ago, there are quite a few protons that are going at different Larmor frequencies, so the signal to begin with is not very strong. Now let's go back to the image, and let's say neural activity gets triggered by some stimulation. And now, again, what happens to the field around the venule? Well, it'll probably get smoother. So if the field gets smoother, what happens to many of these protons out here? Well, they are no longer inside a different magnetic field compared to the orange protons. So now most of these are resonating exactly the same at the same orange Larmor frequency, whatever that might be. Of course, again, there still are some protons that are affected, particularly by the intravascular component and whatever deoxyhemoglobin is still inside here. But so what happens in terms of this graph right here? Well, the signal will now be much stronger. I mean, there were some, I think, 15 or 16 protons that used to be in a different magnetic field, and so used to dephase, used to lose pace and dephase faster compared to all the orange protons, that now are instead resonating together with the orange protons. So there's a big change in the signal between rest and task, between rest and active. So it makes sense that, in fact, most of the bold signal is coming from these slightly larger venules. The change between on and off is just so much more noticeable around venules than it is around capillaries. There is around capillaries, we can see it, but it's just much smaller, so it's much harder to see. So, sort of to summarize this, the change in oxygen saturation between the rest condition and the active condition is just much greater inside and around larger blood vessels than it is inside and around capillaries. In other words, the change in smoothness in the magnetic field, and hence the strength of the signal between rest and active, is just so much larger around venules than it is around capillaries. So we can see the change between when some part of the brain is not engaged in any greater neural activity than usual, versus when a part of the brain suddenly starts bursting with activity. We can see that change is just so much more noticeable around the venules than it is around capillaries.